Hey guys, this is a video that I made for the Math Learning Center and I'm going to use it for our class. So here it is. In this sequence of videos, we're going to look at change of coordinates in 2 dimensions. This is the 2-dimensional analog of doing U substitution in Calc 1. So we're going to begin by reviewing the U substitution rule from Calc 1. It's typically written as the integral from a to b of the function f of u of x times u prime of x dx is equal to the integral from u of a to u of b of f of u du. To make this look more similar to the 2-dimensional version of change of variables, we're going to write this in a similar but different looking way. And we're going to start by changing the way that we write the domain of integration. And we're just going to make it look more like the way we've been writing it for Calc 3 integrals. So instead of having superscripts and subscripts on the integral, we're just going to have subscripts on both of them. So the integral from a to b is the same as integration over the set a comma b. And integration from u of a to u of b is just going to be integration over the image of a to b under the transformation u. So this interval, this notation, u of the interval a to b, all that means is the integral from u of a to u of b. The next thing that we are going to do is going to seem pretty strange at first, but when you see the change of variables rule for 2-dimensional integrals, I think that it will make a little more sense. What we want to do is move the u in the subscript of the integral on the right-hand side to the left-hand side. To do this, we're going to say that the interval u of a to b is equal to the interval c to d. And so on the left-hand side, we're going to have u inverse of the interval c to d, and on the right-hand side, we're just going to have the interval c to d. To be a little more precise, we're saying that u of a is equal to c and u of b is equal to d. And now what we're going to do is going to seem even stranger than that. We're just going to swap u and x. So all of the u's will get changed into x's and all of the x's will get changed into u's. We'll begin by changing all of the u's into x's. And so we don't lose track of what we've done, we're going to make them into red x's. And all of the black x's now will become blue u's. And so now we're just going to write this u substitution rule from Calc 1. Now remember, this does not look like the normal u substitution rule from Calc 1, but we started with the normal rule from Calc 1, and by making various changes, step by step, we came up with this similar, or actually equivalent, u substitution rule from Calc 1. Like I said, it looks different, but this is more consistent with how we're going to need it to look for doing u substitution in 2 dimensions. In Calc 1, we normally begin with the integral that's on the left-hand side and transform this to the integral on the right-hand side because that is typically an easier integral to do. In Calc 3, it goes the other way. We'll start with a 2-dimensional version of the integral on the right and end up with an integral on the left. As a matter of fact, you've seen something similar to this in Calc 1. For example, when you do trigonometric substitution, you begin with the integral on the right and you end with the integral on the left. In this video, we're not going to see the 2-dimensional version of u substitution. We have to get some groundwork done first. So we're going to begin by doing this problem here. And I first need to point out that there is actually a typo. So x is equal to u over 2 is correct, but it should say y is equal to 3 times v. So let me change that now. In this problem, we have 2 things. We have a curve in the xy plane given by x squared plus y squared over 36 is equal to 1. And we have a transformation going from the uv plane to the xy plane. What we want to determine is what is the region in the uv plane that gets transformed to the corresponding region in the xy plane. So again, we have this region, or this curve, x squared plus y squared over 36 is equal to 1. This is an ellipse in the xy plane. And we have this transformation, x is equal to u over 2, and y is equal to 3v. We want to know what curve or what region in the uv plane is transformed into this ellipse in the xy plane. So this is what we might call an inverse problem. We know the output, we know the function, now we want to find the input. Let's begin by sketching this curve in the xy plane. It's an ellipse. It is longer on the y-axis than on the x-axis, and the y-intercepts are plus and minus 6, and the x-intercepts are plus and minus 1. Of course, we'll begin by drawing the u and v axis, and we'll draw this in orange so we can keep track of what's going on. This is the u-axis, and the vertical axis is the v-axis. We'll call the transformation from the uv plane to the xy plane t. And the formula says that t of uv is equal to u over 2, 3v. That is, these are just the coordinates for x and y. So to do this, we're just going to write the equation, the xy equation, in terms of u and v. So x is u over 2, so this becomes u squared over 4. Y is 3v, so this becomes 9v squared over 36, and this is equal to 1. But observe that 9 over 36 is equal to 4, so this becomes u squared over 4 plus v squared over 4. That is, u squared over 4 plus v squared over 4 is equal to 1, or u squared plus v squared is equal to 4. So this just gives a circle of radius 2 in the uv plane. So in other words, the corresponding image in the uv plane is a circle of radius 2 centered at the origin. So what we're saying is that the circle of radius 2 in the uv plane is mapped to this red ellipse in the xy plane under the transformation t. In the next video, we'll do problem 2. And in the video after that, we will look at the two-dimensional version of the U substitution.